This training module describes the importance of total impervious fraction for defining the volume and timing of runoff and defines methods for estimating impervious fractions. This is training module 2.06a for the Stochastic Empirical Loading and Dilution Model SELDM. This presentation has 18 slides and will take about 15 minutes. It was prepared by the U.S. Geological Survey in cooperation with the Federal Highway Administration. This training module has 5 learning objectives. At the end of this module, you should be able to describe the total impervious area variable, identify components of total impervious area, describe relations between the total impervious area and runoff volumes, describe relations between total impervious area and the timing of runoff, and describe methods for estimating total impervious area values for a highway site and the upstream basin. This presentation is a brief overview of the technical details for estimating and using total impervious area values for runoff quality analyses. Please see the SELDM Storm Flow Report, FHWA HEP 09005, and the SELDM Manual, USGS Techniques and Methods Report 4C3 for details. Appendix 6 in the SELDM Storm Flow Report, titled Overview of Methods Used to Estimate Imperviousness in a Drainage Basin, provides detailed descriptions with references to the literature. This is a schematic diagram of a basin in map view showing selected components of the total impervious area. The total impervious area is used to define the volume and timing of storm flow from the highway site and the upstream basin. The total impervious area is defined as the proportion or percent of contributing area occupied by anthropogenic impervious surfaces, which primarily consist of pavement and roofs. Total impervious area, or TIA, can be expressed as the fraction 0 to 1 or the percentage 0 to 100 of the total drainage area. SELDM uses the impervious fraction to define the TIA of the highway site and the upstream basin. TIA is an important explanatory variable for characterizing rainfall runoff transformations because impervious areas can rapidly convey precipitation towards the drainage channel network. The total impervious area primarily consists of roadways, buildings, parking lots, driveways, and sidewalks. This map image shows an aerial photograph with the different areas digitized, coded, and colored. As you may imagine, manual digitization and quantification at this scale for many basins would take a lot of work, so other methods have been developed over the years. This graph shows the effects of increasing TIA on simulated runoff coefficients. As you can see, the effects of imperviousness on the population of runoff coefficients are not linear. This graph shows the runoff coefficients generated using the equations developed for non-highway sites in SELDM. The runoff coefficients vary from 0 to 1 on a linear scale on the vertical axis, and the exceedance probabilities vary from 0.1 to 99.9 on a nonlinear probability scale on the horizontal axis. The alternating blue and yellow lines show the population of runoff coefficients generated for TIA values between 0 and 100% with a 10% interval. The mean runoff coefficients increase gradually with imperviousness below 55%, so the lines for the low TIA values are closely spaced. Below a TIA value of 55%, misspecification of TIA by a few percentage points does not have a large effect on runoff coefficients. The standard deviation of runoff coefficients does not change much with respect to TIA, so there are not large differences in slope among the different runoff coefficient populations. This graph shows one stochastic realization using different imperviousness values. However, many similar runoff coefficient populations may be generated by using this approach. The basin lag time is the time between the centroid of precipitation and the centroid of runoff flow. The effect of TIA on basin lag time, and therefore the duration of runoff from the highway site and the upstream basin, is exponential. This graph is a scatter plot showing the basin lag time data from 896 sites across the United States and regression equations developed using the basin lag time, the basin lag factor, and the total impervious area in percent measured at these sites. The vertical axis shows the basin lag time in hours, which ranges over 4 orders of magnitude from less than a minute to more than 4 days. The horizontal axis shows the basin lag factor, which is the drainage length in miles divided by the square root of the slope, which is measured in feet per mile. The alternating yellow and blue lines show the effect of TIA selection on lag time. The lines are tightly packed at low levels of imperviousness, indicating small changes in lag time with a change in TIA. The differences increase substantially as TIA exceeds about 70%. However, because most highway and urban runoff sites are relatively small, the difference in lag times are much smaller than an hour. We should try to derive the most accurate and defensible TIA estimate as possible, but the difference between adjacent TIA values probably is not critical for many small highway sites or for many upstream basins. The TIA may be used to calculate the basin lag time with the equation shown in this graph if a value of -1 is entered for the basin development factor on the highway site form or the upstream basin form in SELDM. The TIA of the highway site is relatively easy to estimate using plans, maps, or photographs because these sites are usually relatively small, well contained, and visually distinct from surrounding areas. This map shows 2 highway bridge decks as highway sites. The boundary delineating the drainage area on each bridge is shown as the yellow line. The impervious fraction would be 1, which means 100% imperviousness. Land cover datasets give pixel-by-pixel values for use in Geographic Information Systems. This map shows a hand-digitized impervious dataset on the left and the equivalent rasterized impervious data from the National Land Cover Dataset, NLCD, on the right. In this case, the lighter areas are more impervious and the darker areas are more pervious based on the amount of pavement and rooftop area in each cell. Such data are difficult to process manually, but are a powerful tool when used with Geographic Information Systems. This image also is useful for comparing the size of an NLCD pixel, which is about 30 meters on a side, or 900 square meters, to the size of a residential cul-de-sac. There are 2,878 such pixels per square mile of drainage area. This slide shows the watershed delineation for Upper Pine Run from the StreamStats application for Pennsylvania and the Basin Characteristics Report for the delineated basin. This basin is upstream of the Federal Highway Administration Highway Runoff Monitoring Site near Harrisburg, Pennsylvania. For the upstream basin, the online USGS StreamStats application can deliver total impervious area with other SELDM basin properties. StreamStats indicates that the NLCD 2001 imperviousness value for this basin is 0.9%. The percent developed area, which is more coarse than the land use distinctions, can be used to generate manual estimates of TIA from GIS, StreamStats, or manual map estimates of developed area. This graph shows measured values of the fraction of TIA on the vertical axis and the percent developed area, PDA, on the horizontal axis. The data are from 262 stream basins in 10 metropolitan areas of the conterminous United States, with drainage areas ranging from 0.35 to 216 square miles and PDA values ranging from 0.16 to 99.06%. This approach can be used for manual analysis because developed areas can be identified as relatively large blocks of disturbed land. This method also may be used with the results of automated measurements. In some states, the USGS StreamStats application provides an estimate of developed area, but does not provide an estimate of imperviousness. This map shows the watershed delineation for Upper Pine Run near Harrisburg, Pennsylvania from StreamStats. The percent developed area estimates for this basin from StreamStats are 1.7 based on the 1992 data and 4.4 based on the 2001 data. The TIA estimates calculated for this basin using the regression equation are 0.3% for the 1992 data and 1% for the 2001 data. In comparison, StreamStats indicates that the NLCD 2001 impervious value for this basin is 0.9%. In this case, the developed areas are small and distributed. The percent developed area may be easier for manual calculation if developed and non-developed areas are segregated and therefore can be easily delineated. This graph shows measured values of the road density, RD, and total impervious area, TIA, for 6,255 stream basins in the United States with drainage areas ranging from 0.62 to 19,229 square miles. The vertical axis shows the impervious fractions from 0 to 1 on a logarithmic scale with values that range from 0.0001 to 0.63. The horizontal axis shows the road density on a logarithmic scale with values that range from 0.01 to 30 miles of road per square mile of watershed area. Although there is substantial uncertainty in road density-based estimates of TIA, especially in rural areas, the graphs showing the relation between TIA and storm flow properties are not sensitive to variations in TIA estimates when TIA is low. The graph shown in this slide also indicates that at the basin scale, most of the upstream basins will have relatively low TIA values. This map shows the watershed delineation for Upper Pine Run in Pennsylvania from StreamStats. The road distance in this watershed, shown as yellow lines, is about 1.8 miles, and the drainage area is about 0.5 square miles, which results in a road density of 3.6 miles per square mile, and an impervious fraction estimate of about 0.021 or 2.1%. In comparison, the StreamStats estimate is 0.9% impervious area. Although the road density estimate is more than twice the NLCD estimate, the difference of 1% TIA does not make an appreciable difference in the runoff coefficients or basin lag when TIA is this low. This graph shows measured values of the population density, PD, and total impervious area, TIA, for 6,255 stream basins in the United States with drainage areas ranging from 0.62 to 19,229 square miles. The vertical axis shows the impervious fractions on a logarithmic scale with the values ranging from 0.001 to 0.63. The horizontal axis shows the population density on a logarithmic scale with values that range from 0.02 to 13,392 persons per square mile. Although there is substantial uncertainty in population-based estimates of TIA, especially in rural areas, the relation between TIA and storm flow properties are not sensitive to variations in TIA estimates when TIA is low. Therefore, minor misspecification of TIA may not have a substantial effect on generated runoff coefficients and lag times. The U.S. Census Bureau Tiger map tool provides coarse resolution data to estimate TIA manually or by using GIS. This map shows the census blocks near the Federal Highway Administration Highway Runoff Research Site near Harrisburg, Pennsylvania. Pine Run, the upstream basin, which has an area of about 0.5 square miles, is delineated using a black line and is identified by the black arrow in the upper left quadrant. This basin is in local census block 113.01. The map scale indicates that the northern border of this block is about 3.8 kilometers long, or about 2.4 miles long. In this case, the imperviousness of the basin can be estimated from the population density of one census block. In densely settled areas, or for large basin, you may need to develop area-weighted averages of 2 or more census blocks. The total area of census block 113.01 is 14,392,121 square meters, which is equivalent to 5.56 square miles. The 2010 population is 4,474 people, so the population density is about 805 people per square mile. The population density regression equation yields an impervious fraction estimate of 0.079 or 7.9%. In this case, the population estimate for the study basin is an order of magnitude higher than the 2001 TIA value from StreamStats, which was 0.9%, because much of the basin is on the sparsely settled hill slope. However, estimates for this stream, Pine Run, and neighboring Sears Run, down at the confluence with the Conchina Creek, are 6.5 and 8.9% respectively. These two basin delineations include much of the census block and therefore more closely match the census-based estimate for TIA. In this training module, we learned that the total impervious area is defined as the percent or fraction of contributing area occupied by anthropogenic impervious surfaces. The TIA primarily is comprised of roads, buildings, parking lots, driveways, and sidewalks. Regression equations relate the average, standard deviation, and skew of runoff coefficients to the total impervious area. These values are used to generate the population of runoff coefficients used by SELDM. The change in runoff coefficients with increasing imperviousness is small for low TIA values and increases as TIA gets large. A regression equation was developed to calculate the basin lag time from TIA values as an alternative to the basin development factor. The basin lag time is a primary control for calculating the timing of runoff from the highway site in the upstream basin. As with the runoff coefficients, the change in basin lag time with increasing imperviousness is small for low TIA values and increases as TIA gets large. The easiest way to get an estimate of imperviousness and other basin properties is to use the USGS StreamStats web application in states where it is available. If you have GIS skills, the National Land Cover Data Set from the national map can be used to derive TIA estimates. If you do not have GIS skills, TIA can be estimated from land use areas, the percent developed area, road density, or population density. Appendix 6 in the SELDM Stormflow Report provides detailed information and regression equations for each of these methods.